Hello, this is Mr. Stansbury. I'm going to take you through the notes on the binomial distribution. At the end of this, you should be able to say, I can use the binomial distribution to solve various problems. Okay, first thing. In a binomial experiment, there are a fixed number of independent trials. So meaning independent trials, remember, means that one trial does not have an impact on another. So like flipping coins are independent trials. Okay? There are only two possible results for each trial. Okay? Success is if some event occurs, or failure if the event does not occur. So like success could be flipping a coin getting heads. Failure could be flipping a coin and getting tails. Okay? Probability of success is the same for each trial, hence independent trials. Okay? If X is the number of successes in a binomial experiment with n trials, each with probability of success P, then X is a binomial random variable, which I know to a lot of you are like, what does that mean? So glad you asked. Let me show you what that means. Okay, this is a problem from earlier on. For most of us, it's on page 3. It starts on 347. Okay, but it says, consider the spinner on the previous page. Suppose a success is a blue result, and let X be the number of successes in 3 spins of the spinner. So success is when you were getting blue. Okay, X is a binomial random variable with n equals 3 and P equals 3/4. So n equals 3. That means we're going to do 3 spins. And then the probability of what we're calling success here is 3 of the 4 sides are going to end up spinning blue. So this is probability of 3/4. That's the probability of spinning a blue. Okay, so that's what those mean. And then they can take the value 0, 1, 2, or 3. So that means 0 blues, 1 blue, 2 blue, or 3 blues are the 4 possible outcomes. To help determine the probability distribution of X, we first draw a tree diagram, this thing here, and find the probabilities associated with each possible outcome. Okay? And then we let B represent blue and W represents white. So this one here, 3/4 of the first spin, we should get blue. 1/4 of the first spin, we should get white. And then on the second spin, it doesn't matter what we got on the first one. 3/4 blue, 1/4 white, so forth and so on. Okay? So the outcome on this branch right here is blue, 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 hence BBB. Okay? And the probability of that happening is 3/4 times 3/4 times 3/4, which is 3/4. There's our 3/4 times 3/4 times 3/4 cubed equals 0.422 if you calculate that out on your calculator. Okay? And then over here I put just number of blues. So we had 3 blues, 2 blues here, 2 blues here, 1, 2, so forth and so on. Okay? So like let's say this path right here. Let me do this in a different color and make it a little bit easier to see. So let's just say this path here was this, this, and this, right? So we got a blue. The first one was blue, 3/4. Second one was white, 1/4. Third one is white, 1/4. So if we multiply those all out, that's 3/4 times 1/4 squared equals 0.047. So that's going to happen about 5% of the time. Okay? And that's where we end up getting 1 blue. Just so you can kind of understand what that means here. Okay? And then also with that, to kind of help maybe take a little bit different spin on this here, this is going to be, I just numbered these outcomes 1 through 8. So this has nothing to do with, like, it's not the number of possibilities. It's just the first outcome we're going to say is blue, blue, blue. Second outcome is blue, then white. Third outcome, blue, white, blue, so forth and so on. Okay? So the way this is written, P of 3, so that's a probability of being successful 3 times. That's 3 blues. Equals 1 That 1 refers to this one over here. So this is there's only one path that we can get to that, and it's this one up here. That's 3/4, 3/4, 3/4, which is 0.422. Probability of getting 2 blues, we can either take path 2, path 3, or path 5. That's what the 2, 3, and the 5 are. So really it's 2, 3, and 5. Any one of those 3 would work. So we add the probability of path 2, which is 0.41, plus path 3, which is 0.141 also, and then path 5, 0.141. So we just did this, 0.141 plus 0.141 plus 0.141 gave us 0.422. That's another way we could have gotten that. Okay. Those are 3 different ways we can get 2 blues. The probability of getting just 1 blue is either path 4, 6, or 7, right? So we add those 3 all together to get 0.141, or the probability of getting no blues, the only way we can do that is path 8, which is 1/4 times 1/4 times 1/4, which is 0.016. And these are all rounded numbers here. Okay, so hopefully that's making a little bit of sense. Okay, and we're going to take a little bit closer look at this. Okay, we can actually simplify our tree diagram to only consider the value of X, the number of blues. And then it's just assume that the other ones are failures, which in this case is white, okay, after each spin. So we could do this. Our tree diagram could be like, here's where we start. The first spin can either be blue or white. So this would be blue. And then the second spin, if the first one was blue, we could either get blue or white on all of those branches. Hopefully you'll recognize that. Okay. And then we're kind of counting up the number of blues as we go. So on this one here, we're at 1 blue, 2 blues, 3 blues. This branch right here, we ended up with just 1 blue because it was blue, white, white. Okay. Now, something important to kind of take a look at here is the number of paths to get to this spot here. So really, like this, to end up getting 3 blues, there's just one. I'll use the same colors as this over here. There's one way to get 3 blues, and that's blue, blue, blue. This here, there's actually 3 different paths we could take. We could go blue, blue, white. We could do blue, white, blue, or we could do white, blue, blue. So there's 3 ways to get there. This one here is also got 3 paths. We could go white, white, blue, white, blue, white, or blue, white, white. There's 3 ways to get that. And to get all whites, there's only one path. That's what this 1331 here is standing for. Now, this thing here is actually going to form something called Pascal's triangle. Okay? You can find the next row of numbers of Pascal's triangle by adding the 2 numbers diagonally above it. Okay, so going back a little bit here. So this first one here, there's just, we always start with our 1 here. There's 1, our first start here, that's the only way, there's only one option when we get to the beginning here. Okay, now to get this first blue, there's one way to get that. And then to get the first white, there's only one way to get that. And then this one right in here, we could either go blue, white, or we can go white, blue. So there's actually 2 ways to get to that, right? And then underneath this here, to get to these here, that's where we got our 1331. So if you look at these numbers here, we find the next row by adding the numbers, the next row of numbers by adding the 2 numbers diagonally above it. So if we look at these things here, we go 1 plus 2 gives us 3. 1 plus 2 gives us 3. 1 plus nothing gives us 1. 1 plus nothing gives us 1, right? So with that, actually we've got 1, 1, and another 1 up here if I'm doing Pascal's triangle the right way here. Okay, this here doesn't entirely work for what we're talking about here, but the rest of it will all fall in place. So if we end up doing another row here, there would still be just one way to get all blues. And then if this was blue, 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 white, there would actually be 1 plus 3. There'd be 4 ways to get that. 3 plus 3, there'd be 6 ways to get these numbers here in the middle. 3 plus 1 here gives us 4. 1 plus nothing gives us 1. So this Pascal triangle can go on forever and ever. Okay, we won't need it to, but you at least kind of want to know how Pascal's triangle works out here. Okay, we're going to call this good for the first half of the binomial distribution. We're going to cover the rest of the material on the second video. Okay?